Thank you for coming. I'm Trevor. I'm here to talk to you today about how we got some ADCs going really fast in the IIO subsystem of the kernel. So a quick agenda for this talk. I'm going to give an intro about the BayLibre and myself before jumping into some details about the background context for the project. Talk a bit about a couple of features in some subsystems, SPI offloading and what I've dubbed PWM overloading, just as a bit of a pun. Then go back to talking about some ADCs operating at full speed before finishing off the talk with reflecting on a developer Q&A that I did internally. So an intro. So if you don't know who BayLibre is at this point, we're a services company specializing in all things embedded and tool chains now as well. We're based in Nice, France, but we're all over the world. I'm actually outside Ottawa in Canada. I'd say a little over half of the company is based in Europe. We're a Linux Foundation member, a silver level, lots of regular open source contributors and maintainers on the team. If you want to know more about us and find out what we're doing, you can visit the website and check out our blog where we list all our technical accomplishments. So about me, I'm an embedded Linux developer. As I mentioned, I'm based in the Ottawa, Canada area. I'm a maintainer primarily for parts of the Octo project, a lot of Python recipes, and also an automated tool called Patch Test. My background is largely in Python and automation, and now I'm doing kernel work too. This was actually my first experience doing development for the kernel, and I joined BayLibre in April 2023. So this part is just an overview of how the project came about and how we got set up to do all the development that we ended up performing. So background, in mid-2023, BayLibre began a contract with Analog Devices for driver development in the kernel, as mentioned, some subsystem improvements and documentation. There was a lot of Python and MATLAB support added as well, along with some bare metal work being done, but this is kernel talk, so I'm going to stick mostly to that. It was a team effort. We worked closely with ADI developers and doing a lot of testing with them. BayLibre is a remote-first company, so we had some technical challenges when it came to sharing access to hardware that we had to resolve. If you want to know more about that, I've linked a few different talks that some of my colleagues have given in the past. The first one in particular covers the hardware setup and talks about some of the resolver work that David did. There's also Uva's talk on the PWM subsystem from last year, and David's talk in Denver earlier this year too about SPI offloading. So target devices for this project, there were about 121 in all that we had to deal with in the kernel. Almost all of these were ADCs. There were a couple of resolvers and about a dozen DACs as well. And the image there is just a screenshot of a spreadsheet we used to keep track of all the parts, then all the characteristics they had. There's a ton of columns off to the right that were cut off here. I had to cut it off, otherwise you wouldn't be able to read anything. Probably can't read that much as is. But yeah, all sorts of different features we had to consider. Every family was unique in its own way. So there were a lot of common features we had to address in the IIO subsystem, but then when it came to specific drivers, there was always a lot of customization needed. So as for the hardware setup, I had some hardware on my desk. This is just an image of my Z board and one of the eval boards that we did development for. That one's for the 804000 series of ADCs, which are a mix of differential and single-ended boards. Yeah, so that was a Z board running Kuiper Linux OS, which is Debian-based. I think it was Debian 11 when we did the development. I used some test tools like a Rigel DS1054Z oscilloscope, Sigilant waveform generator, and a Salier logic analyzer. After the main leg of the project, actually to prepare for this talk, I started using LabGrid to do some automated control of the board. If you want to know more about how what might get done, I actually have another talk right after this in G104. And just as a side note, some of the other developments, namely Uva worked on a D10 Nano for a couple of the drivers and used a straight Debian spin instead of Kuiper Linux. Just for comparison, so the hardware setup, I mentioned we were remote first, so we had to share remote access to a lot of the Z boards and the development boards that were attached to them. How we did that, We're still using mostly the same setup. Instead of having discrete test equipment, we used what's called the ADLM 2000 or the M2K, which is just a handy all-in-one tool for that, produced by ADI. It's got some nice software called Scopy you can use with it. For power control, we used what's called the BayLibre Copilot. It's basically just a GPIO-controlled power pass-through. And a few of the devices, again, I linked David's first talk from 2024 a few slides before, were actually tested with a Raspberry Pi as well, and you can check out the ADI wiki for more details on how that got set up. So software setup on my side. For building the kernel, I used a Debian 12 system based on a Ryzen 7900 processor. For building the HDL, when we had to do that ourselves, we used Vivado, which was pretty heavy. It actually made this particular laptop lock up more than once. Measurement, in addition to all the actual hardware test equipment, I used IIO oscilloscope, which is another ADI tool just for monitoring signals over the network on the Z board, and as I mentioned, Scopy, which is the interface to the M2K. We had some bash scripts just for making it more convenient to do builds. For the PWM side of things, we used libpwm, which is UVA's test tool, and I mentioned before, just to plug the next talk to, LabGrid to do some automated control. So an acronym you're going to see a little bit in some later slides is AXI, which stands for Advanced Extensible Interface. It's a Xilinx protocol for memory mapped I/O. What you can do with that, you can implement a variety of interfaces in an FPGA, such as a SPI controller or a PWM generator, which is what we actually ended up writing some of our drivers for. ADI maintains a repository of HDL source code for that. You can take a look at, again, another link I've got there with a guide for setting it up. The important thing to take away from that is that you build that HDL into a boot.bin, which you need along with a UImage and a device tree and obviously a rootfs to actually bring the Z board up. Finally, just a little bit of info on the IIO subsystem. If you don't know what that is, there's some documentation linked. The maintainer is Jonathan Cameron. It's basically where drivers for a variety of different sensors live. These usually use a variety of different clocks, PWM signals, and interfaces like SPI and I2C to become controlled and configured. They usually have some sysfs parameter access available. That's how we actually did a lot of the very rudimentary testing when we were first bringing up drivers. So the majority of our work was focused on the IIO subsystem, but in order to actually get drivers written and working, we had to do a lot of work elsewhere, and that's what I'm going to talk about next. So the first part is SPI offloading. This I'm also going to cover very briefly because, again, David gave a talk recently that covers it really well. I highly recommend watching that one. The takeaway, the main goal of adding the SPI offloading capability was to reduce the burden on your Linux system by offloading SPI transactions to hardware that was dedicated for it, again, in this case, an FPGA. Just an example of why you'd want to do that, we have some devices, the 87469X family, most of them really operate on very short time scales on the order of nanoseconds in order to trigger conversions. So it's going to be hard to achieve that consistently on your Linux host if the CPU is doing anything else. And I mentioned earlier the AXI SPI engines. We wrote a driver for that. It took about a year to actually get all that upstream, all the capability. Many rounds of reviews. You can look that up on the mailing list and I think see 11 or 12 different revisions. But once that was in, we could actually achieve mega samples per second with the ADC devices without taxing the CPU too heavily. And I've got some links here just in case someone wants to go look at the specifics. So 5 different drivers covering about 50 devices in all, different max sample rates. Almost all of them, the SPI offloading was added in either kernel 6.15 or 6.16. I've got commit IDs there. If you want to go look at how the feature was added for a specific driver. This is probably not the extent of the devices that support SPI offload at this point. But yeah, 50 examples to take a look at. Now I'll move on a little to PWM, what I call overloading. There was quite a bit of work here. So why would we care about PWM in this case? So there's another family of devices. There were 4 chips in this family, and I actually ended up writing the driver for this, as we'll see later. It had a very high sample rate. Some of the devices in the project were on the order of 10 kilosamples per second or something like that, but these ones went up to 10 megasamples per second. And they use PWM signals actually to trigger conversions. Specifically, you have to have 2 of them on 2 different pins, and they have to be offset, which is not something that the PWM subsystem supported when we started this project. And this is just a diagram I added to show how everything's connected, at least on that side. There's a very similar diagram in the documentation in the kernel in ASCII. This is a diagram for the timing spec taken right from the datasheet for the 807626. It's not quite accurate because the signal in pink that I've highlighted should actually be matching the clock pulses, but it's illustrative to show you how the offset actually had to work. And in particular, the clock signal had to be offset by the maximum value for TMSB, just to ensure that data was actually available after the conversion was triggered. So yeah, we had to add support in the PWM subsystem so that we could actually do this. So I mentioned that when we started this project, the PWM subsystem didn't support offset. This is the standard format and the characteristics that a PWM could have when we started. 2 main attributes, period and duty cycle. You might also care about polarity, enable and disable, and what's called usage power, which is if it's a Boolean that just, if you enable it, it just gives the PWM a little bit more freedom as long as it operates within a certain power window. But yeah, and I have a diagram here, just 2 examples of PWMs, the same period, different duty cycle. That was the kind of thing you could configure in the kernel at that time. So getting started, in order to ultimately support the 762X and 796X devices, we had to follow 4 steps. We had to get a basic driver going for the AXI PWM gen, which again is the PWM protocol implemented in the FPGA. We had to then add support for PWM offsets in the PWM subsystem. Had to refactor that driver to use that functionality, and then finally we could actually write the ADC driver. The basic driver for the PWM gen interface landed in kernel 6.11. There were a couple fixes that were submitted shortly after just to make sure that all the device properties were available in sysfs. Then we went ahead and modified the PWM core. I wrote an RFC in a V2 that in principle worked. I tested them. It did work without my driver, but the unfortunate side effect, if that would have been accepted, is it probably would have broke almost every other PWM driver in the subsystem. So, proof of concept, but we had to do more work to get it to really work nicely. Uwe did that. He joined BayLibre about that time and got that merged finally in 6.13, which included the aforementioned offset support in the PWM gen driver. So as of 6.13, you now have 2 options. The state option I mentioned before, still available, still used in a lot of drivers, but alternatively, you can use what's called the PWM waveform, and it only has 3 attributes, period, duty cycle, and what we call duty offset. These are all specified in nanoseconds. And I've got a similar diagram just to illustrate what that actually means. Your PWMs no longer have to line up when you enable them. That's the big takeaway. And you can represent signals that you would see before with inverse polarity just by doing a little bit of arithmetic, nothing too fancy. And you can actually represent disabled PWMs with period 0, which was otherwise an unreachable state. Yeah, and this, I've just taken some screenshots directly from the PWM header just to show you how they're represented. We actually added the NS suffix just to make it more clear what the units are. But again, both of these are available depending on what your driver needs. They're both, you can use either one now. So I don't want to make it seem like it was a very simple process. It was actually quite a complicated development sequence. One of the big challenges we had, and Uwe talked about this extensively at OSSEU last year, was that we had to handle rounding effectively. So we derive PWM signals from the system clock, but depending on how your system clock operates, you can't necessarily just, divide it and get any frequency you want. So there's going to be some rounding involved. And some early versions were actually rounding up, or not rounding to giving you the expected value that you request for the PWM. So he had to implement some rounding functions to make sure that when you requested a certain value, you didn't exceed anything, you were getting something you could actually predict reliably. And I just copied from the second patch in the series he ultimately submitted the logic that he followed for doing the PWM rounding in the subsystem. Basically, you want to make sure for every one of the three properties that you're not going over the requested value. Which means in some cases you're not getting the ideal signal, but you can compensate for that in other ways. When it comes to testing the duty offset, the manual method that I followed, so I showed the Z-board setup I had on my desk at home. What we do, there's a custom version of the AXI PWM Gen FPGA load that would be built, but we route the PWM signals to one of the PMOD headers, basically, kind of like a GPIO, and I would attach that to an oscilloscope and then set parameters for the PWMs in the kernel and check to make sure that things were coming out as expected, in particular offset, but also that there weren't any strange rounding effects or anything like that as well. On the next slide, I've got a diagram to illustrate that. I've got the yellow channel attached to PWM 0 and the blue channel attached to PWM 1. Both of them have the same period length and duty length, but one of them has an 8,000 nanosecond offset that I've requested. And there's the diagram. So there's a bit of an Easter egg in this slide. If you looked at this ahead of time or you're looking closely, you'll notice I've labeled that offset is 8,000 nanoseconds, and that's what the cursor says. But in the bottom left, the oscilloscope is actually measuring 7,950 nanoseconds. So there's an example of the rounding effect showing up on the duty offset. I actually didn't catch that until last night, so surprise. Okay, so that was a bit of a whirlwind about SPI offloading and the PWM changes. I hope I didn't go too fast. Now that we had all that supported or added to the kernel, I could finally go back and add the AD7625 driver. I've got a screenshot or an image here just of my signal generator on my desk. This device is a little funny because I was using it to generate anti-phase signals to test this device because it's fully differential. The way the interface looks, you think that I'm only generating one waveform, and I'm actually generating two that are 180 degrees offset. It took me 5 revisions of the patch series before it finally got merged again into 613. And I've got another image on the next slide just showing a capture using IIO oscilloscope, which is a software oscilloscope, capturing a 100 kilohertz signal that I generated with this. And there it is, all nice and clean. I wanted to do a little bit more extensive testing again with my board, but unfortunately I no longer have the evaluation boards for these particular parts on my desk, so I had to copy things from the archive of images that I took when we were doing the initial testing. But yeah, nice smooth signal operating at 100 kilohertz. And just to show you that it wasn't all about just achieving maximum sample rate, this family of parts had an interesting set of configuration options. There were some enable pins, 4 in total. The 87625 and 87626 only had 2 to configure which voltage references the ADCs had to deal with. But the 796X had a total of 10 for a variety of different modes, power down, controlling bandwidth, the voltage references, all that stuff. So we had to handle this carefully in the kernel, in the driver. What we ended up doing is implementing part of this in the device tree bindings. So basically there's a bunch of fields you can specify depending on how your board's wired up to say that certain of these pins are either always wired high or configurable, and if you don't specify them at all, they're assumed to be wired low. And this is just a screenshot from the driver code itself, just to show you what that looks like. Obviously, there's another case of, there's a ton of code, and if I copied it all to show it all to you, it would be way too small to read, but there's a link there if you want to see more. Basically, a bunch of Booleans in the driver struct, and a handful of functions to parse the mode and make a decision about what operating mode the ADC is actually going to be in by default. So I'm on to the last part now. Just want to check the time. I think I'm going pretty fast, but so the last part, this was a pretty big project, and we were working on it for well over a year, and there were lots of us on it. So I didn't want to make it look like this was all about what I did, because I worked a lot on Python support and the driver that I just mentioned, and one more, but there was a lot of good effort being done. So I wanted to do a little bit of a Q&A and get people's feedback on how they felt about the project. So I asked some of my colleagues 4 questions: which kernel drivers they added or modified, if they contributed anywhere else, what was most memorable for them, and what was the most challenging part. And I've summarized that on the next 2 slides. So part 1, for kernel drivers they added or modified, they added new drivers among 6 families. I worked on the 804695 with David, and that one, I didn't cover that in this talk, but that one was also pretty extensive when it came to adding support for oversampling. It was a pretty complicated feature at the end of the day. They also added new features and improvements in 3 more. They contributed it to the kernel in other ways as part of the project, so I've already gone over the SPI offloading, the PWM core changes. There were some convenience APIs added, and a lot of janitorial efforts. Like I've talked about the ADC devices here, or the ADI devices here, but in order to make all these changes, obviously we made a whole bunch of improvements to other parts from other vendors too, just so that things still worked. So there was a lot of work going on. The most memorable part of the process, it had been a little while since David got involved. He's originally spent a lot of time with Lego robots. If you watch his other talks, he'll talk more about that. But I guess it had been a little while since he had last done some kernel development. Uwe ran into some lessons learned when he was doing development for the 807124 driver with the DE10 Nano. Even though that device was supported pretty well elsewhere, he had a lot of trouble getting it to come up okay for that board. So for him, there was a little bit of a surprise that even though he expects the kernel to be pretty solid and well tested, in this case it didn't work out too well. And the devices that work really well on one platform don't necessarily work well elsewhere. There was a feature that I'll admit I don't know that much about that Esteban had a lot of trouble with for the 804030 and 804630. The biggest challenge is these 3 really resonate with me, again, because this was a new experience for me doing kernel development. I again showed a little bit about, showed the spreadsheet early on, just kind of hinting at all the different features we had to consider for the parts, making sure that we handled such a big catalog of parts appropriately. Making the best development choices was really challenging. The IIO subsystem was new to Uwe, it was new to me. So understanding how all that was working while understanding how the drivers had to be implemented for specific ADCs was a challenge. And in a lot of cases, the performance when we were starting to bring them up didn't always match expectations, so it was quite frustrating and hard at times to keep motivated. But all in all, it was a pretty great experience. I really enjoyed every moment of it. For future work, there's still some ongoing support for ADI devices. The ADI guys themselves are doing more development on some of them, and we're still doing a little bit internally. I've got 2 personal goals now that I've done this project. Again, I mentioned the LabGrid talk. I'm going to mention this right after this, but this has really inspired me to start doing more kernel development, in particular on a couple of clickboards that I've got attached to my BeaglePlay at home. More kernel work in general. I thought that was really cool. It was really nice to finally get to work at such a low level. And we've been talking on and off about some other subsystem improvements, namely an IIO trigger API. If you go and look at some of the SPI offloading work that David did, he's actually implemented a SPI offload trigger API, but it's specifically in the SPI system, but there's no reason why it couldn't be a more generic one. So some special thanks to Analog Devices, especially Nuno and Michael, who gave us a lot of advice and were always there when we had complicated questions. David and Uwe for being my mentors as I worked through this project, and obviously the entire BayLibre ADI team. Questions?
Describe a little bit more what the relationship was between the PWM and the ADCs. How is that being used to drive transitions then, state transitions?
Yeah, so you would use one PWM to trigger a conversion, and then the other one had to be used to trigger the actual data transfer after a certain amount of time. Like the device had a kind of a dwell time to wait before it assumed data would be available. That varied a little bit depending on the particular part in the family because the sample frequencies were different, their maximum values were different. So, yeah.
Even if you have an FPGA to process fast samples, where are the samples, or what do you do with the samples? Where do you store them if you need to process 10 mega samples per second, or are you calculating an average, or?
That's a good question. I will admit I didn't look too much into the details of where it was actually being set.
Because the problem is always, customers want to process some kind of signal and get many samples, but the problem is probably not only having a fast clock and a chip or an ADC that's capable of acquiring the samples, but what does Linux do with the samples?
Yeah, I'd have to go back and look to be able to tell you for sure, but I think it's, yeah.
They use them for software-defined radios sometimes.
Yeah.
For software-defined radios sometimes. Some applications, they need as much samples to be sampled. The software-defined radios.
Yeah, but it's either the software needs to process, and then you need to either process them in RAM or do some mathematical operations on them.
Yes, I think that's because here it's just about acquiring and making the samples available to the applications.
Yeah, the samples need to be available somewhere.
Access DMAs there are DMA controllers to the active bus. You can DMA from the SPI port of the FPGA directly from the RAM and directly access the memory of the SPI device. So it's like a real.
So, for example, for software-defined radios, you have like a circuit and buffer where you can fill the memory. That's real time. It's going to override the same buffer again, but it's going to be used by the application for uploading to extract layer 1, 2, 3.
So I have a question about SPI offloading.
Yep.
How do you find yourself dependent on the actual FPGA implementation? Because since I guess it's a 94 from AMD, you probably, how is the implementation of SPI offloading dependent on a specific version of Vivado or?
Yeah, I mean, there was a driver support added for the AXI-SPI engine, but I think the best place to look, it would either be David's talk itself or go look at the commits, because it did vary a little bit depending on the part.
Okay, so there is, yes, it's not uniform.
Yeah, I mean, There were some special considerations for some of them. I mentioned the 84695 when I was doing the development for the oversampling support. We actually ran into an issue with the SPI offloading implementation where sometimes it was missing a few conversions. So we had to add a couple of little tricks in the driver to make sure it actually did wait long enough to catch them. So there are some variations depending on the part. Yeah. Any other questions? Oh. Sorry, I can't hear you very well. There's something about software-defined radio. I can't hear you very well. Something about software-defined radio?
Yeah, it's like a digital tuning. It's present on many analog devices, the chipset, like 9361 and others. We contact analog device many times, but it seems we don't have any patches in kernel about this problem. It's like a delay latency. If you have some information in this new chipset, if you will face of this big problem.
Sorry, I still couldn't quite catch everything. I know I've seen the device number you're talking about. I've seen it in some of their documentation, but I'm not sure on the specifics there. Yeah.
So again, following on the SDR theme, I noticed in your control structure that you've chosen a time resolution of nanoseconds. Quite a lot of lab kit now SDR systems are heading towards picoseconds. So is there a reason why you chose nanoseconds for units?
I think it was more of the practicality of what we needed the application for. We were considering picoseconds at one point. So some of the work we did for the PWM changes were based on some stuff that ADI had in their kernel tree, where they had picoseconds added, but when you looked at it, the resolution never actually got there. They had it mentioned in picoseconds, but still practically it was, for all intents and purposes, nanoseconds. So I think there is definitely some room maybe to add support for that in the future, but nanoseconds was as fast as we got for this project. Other questions? Okay, thanks again.